Hi, everyone. As Dylan said, I'm Ali. I'll be talking about multitasking with D. I'll go over some definitions. I'll say multitasking is not parallelism, but just like me, maybe some people confuse the two. I will still talk about parallelism. It has to happen on a multitasking talk. I'll go through some CPU and OS internals, and then I'll explain what fibers are. I hope there are people who don't know what fibers are, because they are, for some reason, the most recent things that I learned and that I enjoyed. And I think they are underrated, although they are very powerful. Then I'll go through some concurrency features that D gives us, and I'll mention asynchronous input and output a little bit, where fibers help as well. And this whole topic is very confusing. There are so many so many terms close in meaning, or so many related terms. Multitasking, concurrency, parallelism, multithreading, fibers. Are they coroutines, green threads, greenlets, lightweight threads, or user threads? All that kind of terms. So multitasking is just doing multiple tasks, performing multiple tasks, not sequentially, not one after the other, but at the same time, likely in an interleaved fashion. It's certainly not parallelism, not data parallelism, where SIMD instructions help. And we're going to hear a great talk from John Colvin, not today, I think tomorrow. It's not instruction-level parallelism, where CPU pipelining help. It's not memory-level parallelism. CPU caches, TLBs, prefetching, etc. are involved. It's not multithreading, but the last two, memory-level parallelism and multithreading, are used behind the scenes in multitasking. The OS and the CPU give us that help. And this impractical and suboptimal example is multitasking, but it's unusable. If you have two tasks, you can go through to two tasks step by step. Okay, here's parallelism. Not multitasking, but because the purpose here to make your program run faster, even though you seemingly have one task. And it's great for embarrassingly parallel operations. For example, let's say you have an array of images, and you want to process these images. They're sitting in an array. You go through the for each. Normally, let's say it all takes 4 seconds. And with Phobos's standard parallelism module, you just put dot parallel at the end of the array, and magically everything happens 4 times faster, assuming you have 4 cores. So this is parallelism. And standard parallelism module has these other great features, closely related, all based on doing things in parallel to complete your task, elements in your range, elements in your array, processed in parallel. Now there is, as I said, parallelism and multitasking are confused a little, and we have this confusion in our Phobos library. Standard parallelism has a task function which returns a task object, where you can do multitasking yourself. You can assign function pointers to one task and another one, and run them in parallel. Even though you're doing multitasking, you get the help from standard parallelism. Now, I'll talk about a little bit the operating system and some CPU internals. Basically, the call stack, CPU registers, specifically 2 of them. What a thread is, CPU caches, MMU, and the TLB. So call stack is this wonderful thing that we take for granted. We write our function, our program. It starts with main. Main makes a call to a function. That function makes another call to a function. And the program never loses where it is. It's executing, going deeper into function calls, returning from functions, coming out. And everything happens in a call stack, because every function call receives a stack frame. For example, here we have mains. It makes a call to foo. Another stack frame is put on it automatically, mainly a CPU feature, but of course the compiler uses that feature. And this automatic stuff happens and you never lose track of where your program is, or where your program never loses track. This is especially useful in recursion. Here's a function sum, a recursive sum, which you should never use. Use standard algorithm sum instead. So this sum is a recursive algorithm, calls itself with a shorter array each time, passing in the current sum. And for the given 3-element array, there will be these 4 stack frames put on top, and automatically everything goes up and comes down. So call stack is a very useful thing, and we use it in our main program all the time behind the scenes. Then, of course, the CPU does everything on registers. Most CPUs have dozens of registers. Some of them have hundreds. I think Itanium has, and there are renamed registers, all of that stuff. But 2 of them are very, very important, or they take central stage. First one is the instruction pointer, also known as the program counter. This tells us what instruction to execute from the memory. Then there's the stack pointer, which is showing us the pointing where the top of the call stack is, what we just seen. And here's a plug for the mill CPU, because I see that the mill is mentioned on our forums occasionally. It's a revolutionary CPU without any conventional general-purpose registers. It uses what they call a belt. Even that CPU, without conventional registers, has those 2 registers, the instruction pointer and the stack pointer. So the instruction pointer and the stack pointer define what a thread is, or a very simplification of what a thread is. There is other stuff around it. IP determines the execution part of the thread, which is an execution context, and stack pointer determines where the context of executing that code is. There are other things like thread local storage, which I'll get to. So throughout this presentation, I will use this little box to represent a thread, just the IP and the SP. And here's an example. Let's say the operating system is executing 2 programs. A says hello world, B says hello Mars. Of course, being compiled languages, the 2 compiled code put into memory, which is that blue ribbon going from left to right. And 2 stacks are allocated for each main thread. Operating system creates a structure. IP points to the beginning of that compiled code. SP points to the stack. Likewise, B has an IP and an SP. And then operating system knows about these 2 threads and executes the code. Well, let's improve one of the programs and give it another thread, which is very simple in D. This one spawns a greet moon function, which becomes another thread, which, with its IP and SP pointing to the beginning of the compiled greet moon and the stack pointer for that thread. Now, these 2 programs have just 3 threads, which are usually among hundreds or thousands of threads that the operating system is executing at a given time. There are so many of them, and maybe A's main, A's greet moon, and B's main are just 3 of them. But the entire execution happens on the cores that you have. Let's say you have 4 cores. What the operating system does is assigns or sets the IP and SP of one of the cores to one of the threads, likewise, and tells those cores to go ahead, execute. In this example, we have an idle core, which is a bad thing. So the operating system thread scheduler will go out and pull another thread, put it on the 4th core, and run that at the same time as well. So thread scheduling, which means picking which thread to run next, is a very, very complicated algorithm. It relies on what the operating systems define as the process priority, or thread priority of that process, or whether the operating system thinks it's an I/O-bound thread or a CPU-bound thread. Or, this is a Linux thing, whether that thread used up its own time slice fully or not. It determines the thread scheduling. Or in Windows, if you bring a process to foreground, it has a higher priority than others, etc. So here's the thread scheduler, and there was so the main goal of the thread scheduler is there shouldn't be any idle core on the system. If there are runnable tasks, they have to be put on a core and executed, run as soon as possible. And if you search for that article, The Linux Scheduler, a Decade of Wasted Cores by Lotzi and others, they discovered, I think, 3 or 4 issues with the Linux scheduler where some cores were sitting idle unnecessarily, even though they're runnable threads. It's a very interesting read if you're interested in that kind of stuff. So what the thread scheduler does is, once it puts a thread on a core, allocates a time slice for that thread to execute on that core. And there's a time slice, and the thread starts running at the beginning of the time slice. However, in most cases, or in some cases, a thread does not use the entire time slice. It doesn't go all the way to the end, because it stops early, waiting for some input or output event, I/O, waiting for a synchronization primitive. Maybe it needs other threads to get off a critical section of the code. Or sometimes threads pause themselves intentionally, or their owner thread pauses them. In cases where the thread runs all the way to the end, then the operating system comes in and preempts that thread, saying, okay, now it's time for another thread, pulls in another thread on that core, and that gets executed. Are there any questions? You can stop me anytime, of course. So here is a time slice which has not been used fully. The thread started running on the left-hand side, stopped right at that point, and the OS immediately pulls another thread and starts executing it in its place. And this is a performance issue because an actual time that thread, your thread, could have used to execute is abandoned to other threads on the system, to the competitors, if you will. Okay, so any talk that involves the CPU has a picture similar to this one. This is what I've drawn myself. So here's an imaginary 4-core CPU with 3 levels of hierarchical cache. Accessing the actual memory on the system is an extremely slow operation. So these are some typical numbers, but they vary from CPU to CPU. Accessing the physical memory is about 200 clock cycles. Once something is pulled in and put into the level 3 cache, it comes down to 80 clock cycles latency. And then progressively it gets faster and faster, and the very small level 1 cache has just 1 clock cycle access to memory. So as the CPU both executes the instructions or touches data on the memory, all those instructions and the memory are pulled into these caches for quick consumption. And the physical memory is the bad one there. You don't want to go there. To add to this picture, every operating system that matters today uses virtual memory, where every process thinks that it has the entire address range available to it, even though some of them are not allocated. But the addressability-wise, from 0 to all FFFs, all the entire 64-bit range, they look like, they think they own that range. For example, a process A may have a variable X at virtual address hex 1000, or a B has its completely unrelated Y at hex 1000, but on physical memory, those 2 variables may be sitting on completely different places. So the code wants to touch a variable at hex 1000. The CPU is executing that 1000 access, but the thing is somewhere else. So this requires a translation at runtime. As you're executing your code, constantly there is this translation happening behind the scenes from virtual address to physical address. And the CPU is not the tool that does this translation. there's this extra device in between the main memory and the CPU called the Memory Management Unit, MMU, with two main purposes. It does the actual memory access for the CPU and also does the virtual to physical address translation. This virtual to physical address translation is a huge table which cannot fit in memory itself, which may be page to disk itself. So some part of it that can fit on this device is the TLB, translation look-aside buffer, which is extremely fast. So if the address translation fits on TLB, it's just 1 clock cycle. If it's not there, it's 100 clock cycle cost. So as your thread is executing, both the CPU caches and the TLB are warmed up for your application. The caches are filled in, everything is warm, and your thread is going at lightning speed. Everything is happening at 1 clock cycle hit rate most of the time. Then comes the context switch, which I mentioned earlier. Instead of your thread, some other thread comes in. So, well, if we hit the entire time slice end of it, that's a good context switch because we used it all up. As I said, if we're waiting for input or output, apparently, or something else. So what happens is, first of all, you're not using part of your execution time, as I mentioned, but also, as soon as another thread comes into your place on that core, the instruction cache and the data cache are not for the new thread anymore. So that new thread will touch code areas and data areas in memory where they will hit the 100 clock cycle TLB plus the 200 clock cycle cache miss penalties to warm up those caches for themselves. So that's why a context switch is or can be a very expensive thing. So this is the bad thing. So if you leave your context switch to the operating system, if everything you do stays on a thread, you will pay these penalties. Enter fibers. So fibers are coroutines, or that's my definition. Some people disagree. What's a green thread? What's a user thread? What's a fiber? So let's start with this same fringe problem, which was shown back in 1977, I think, as the definitive simple problem that proves coroutines are the great solution for. So here's the same fringe problem. There are two binary trees. Tell me if they have the same fringe, which means if they have exactly the same leaves reading from left to right. So I have two trees. I need to iterate them one by one. And as soon as I see a mismatch, I will say they don't have the same fringe. But I'm simplifying it a little bit and say, let's change the problem to, we have two trees, and let's traverse them in order and see whether they have the same elements or not, in order. They need not be a search tree, so the numbers may be in different orders. So if I've drawn this correctly, these two have the same in-order elements. Okay, so recursive tree traversal is easy and elegant. It's one of the most elegant things in programming, actually. So I have a traverse function that takes a node pointer. I give it a function. If the node is null, we're done. So traverse the left side. After that, apply this element to the function, or apply the function to this element, and traverse the right side. This is wonderful. And regardless of how complicated the shape of your tree is, how deep it is, this works correctly, thanks to the call stack. It'll go deeper and deeper with those traverse calls recursively, and then come back eventually. Everything winds back. But what if you have two trees? Call stack takes care of only one traverse execution. Your recursive function is put on top of your current call stack. What if you have two? It's extremely difficult. So one thing I find striking is it's extremely simple to do recursive, one tree, But once you have a second one that you want to traverse, you can't do it recursively, and it becomes this very difficult task. Here I have a tree struct which has an op slice that returns an in-order range. Exercise to the attendees, go ahead and write an in-order range for a tree, a binary tree. It's pretty difficult. Some implementations like the C++'s STL needs to use parent pointers. So it's not only difficult, it also changes your data structure to introduce a third pointer, not only left-right, but you have to have this parent pointer to show where your parent was so that you can backtrack. Surprisingly complex. So, enter cooperative multitasking. Remember the time slice where we executed only one portion of it and then we gave up our time? What fibers allow us to do is, instead of giving our time back to the operating system to be used by another thread, we ourselves go to another execution context that we may manage, which is a fiber, and we start executing that fiber. So our main thread, instead of giving up the time slice and the potential CPU caches and the TLB caches, switches to a fiber, one of its fibers, of one of 1,000 fibers potentially. Fiber executes a little. When that fiber stops for any reason, maybe I/O related, it comes back to the main thread, and you continue your main execution. Go back to the fiber, go back to the main thread, and main thread and the fiber ping-pong the execution between the two of them. So creating a fiber in D is extremely simple. You need to have a fiber function, which is a good old function which returns void and takes nothing. One way of creating a fiber is with the new fiber class. You just give it the fiber function, and you're done. You have this execution context of a fiber where your main thread can call with this fiber call. And then inside the fiber function, the fiber itself yields execution back to the main thread with fiber yield. So main thread says fiber call, and it says fiber yield, back and forth. And eventually, your fiber can complete its execution and become terminated. There is this state that you can determine whether it's done or not. So actually, what happens behind the scenes is, when you create a new fiber, in user space, in a library, which is our core thread library, a new memory is allocated dynamically, which can be as huge as you want on modern operating systems because it's not really committed to you. You just allocate that much. And that allocated space becomes your stack, call stack of your fiber. Then the address of fiber func is assigned to the instruction pointer, and a little structure where an instruction pointer and this newly allocated stack pointer come together to define your fiber. As you can see, it's not much different from what the operating system defines as a thread. And so they're both the same functionally. And just to repeat, an instruction pointer and the stack pointer make the execution context. So the great thing about this is context switching from your main thread, your fiber, is as cheap as a function call. And almost. There's a little extra cost there. And the great thing is CPU cache, TLB, etc. are not disturbed. Hopefully. There are cases they will be disturbed where your fiber function is completely different from your main thread. The instruction cache will be flushed, of course. Okay, the mandatory Fibonacci series example. So here's an example of a function Fibonacci series. The creation is here. So as I said, fiber is created with a new fiber class, which takes a parameterless void returning function. So that's why we're creating a lambda here. We're passing current variable as a reference to Fibonacci series in this case. And the Fibonacci series sets the current to the current value of the series, starts from 0, 0, 1, of course, and then yields execution back to the main thread. If you notice, the Fibonacci series function has an infinite loop in there. While true, fiber yields a result, or yields execution back to main thread. So fiber call goes into that Fibonacci series. Yield comes back right here, prints the current value, goes back and says fiber call again. Fiber continues at the point where it was yielded from, or it yielded from, and this continues. Even though the Fibonacci series is an infinite fiber, has an infinite loop, because I'm calling it only 10 times, I'll get just 10 values out, and I'll be done. When I exit this scope, the fiber object will be out of scope, destroyed, or garbage collector will do that, and I'll be done. So this is fibers actually multitasking. Even though my main thread can be doing many other things of its own, every time it says fiber call, we switch to that second task and continue with that second task. There are 3 problems with this approach, though. One, there is no range interface. I need to do explicitly fiber call. So there's no front, pop front, and empty primitives on this one. And it uses a reference variable to communicate its result back outside. And also, it's the lowest level fiber API that we have. We need something higher level, more useful. So enter standard concurrency has a generator where I'm aliasing it as a fiber range there. So it's right here. So I'm saying fiber range starts with this Fibonacci series function, and it produces int results. The great thing about this one is it's just written as a simple function. And instead of saying, let me go back, instead of saying fiber yield, it actually says yield this value, the current value, which is a local variable now. This is much better because there is no reference variable, there is no shared data to communicate. And it's also an input range. The fiber range itself provides the front, empty, and pop front functions, so I can pass it to any Phobos algorithm or any range algorithm. Here I'm saying series, take just 10 of those. Even though it has an infinite loop again, I'll take just the first 10 of those. So here's going back to the same fringe problem. What if I want to iterate 2 trees at the same time, or traverse 2 trees? It's extremely simple. Instead of passing the node element to a provided function, I'm just yielding a node element from this fiber. So I can create any number of fibers, hopefully using this fiber range API. And I can have many of these, n number of those, and I can traverse these trees at will. I can say, you go to the next one, you go to the next one, and then I can compare the elements. If they are different, they don't have the same fringe. If they are, I continue until I hit the end, or they differ. And one other thing about fibers is, I'm noticing that I forgot to put on my slides, you do not need synchronization primitives. If you notice, everything happens on the same thread. So main runs, and then fiber runs. There is no concurrent execution at the same time. So you can safely share any variable between the 2 tasks. That's why, actually, there the current reference was used. The reference parameter is either used by the main thread or by the fiber. So they are nicely interleaved. There's no concurrency there. I mean, concurrency is there, but they don't run at the same time. Any questions about fibers?
So that's fascinating. So basically you have the Python yield statement right there. I will never write a proper range structure again, or why shouldn't I use that? So my question is, why is it hidden in concurrency generator somewhere what's the reason for not using it for every input range ever?
I would say, well, this is, first of all, great, because it takes care of that call stack for you, as you note. That's wonderful. I think one of the problems that I can think of, is the stack, the dynamically allocated stack per fiber. Every time you create a fiber, you need a stack allocated for it, because you don't know, and the compiler doesn't know how deep a stack is needed while it's executing. This actually brings another topic where there were discussions on the threads. There is this thing called stackless fiber, which should be called something else, Amaury? Generators, okay. So if the language supported fibers, or somehow understood that this fiber does not make any calls outside of its own local function, then the compiler could know, or the language could know, there's only one level stack depth in here. We don't need an arbitrarily long depth. So in that case, we would not dynamically allocate the stack, but just use some constant area for that stack for its operation and keep it alive. But I'm not a compiler implementer, so I don't know. So that's the one thing I can see there. The other thing is, I passed it very quickly. There's an issue with this, with the current implementation, and if you can find a solution, that's much appreciated. Because the fiber range takes just a function pointer, and the function pointer does not know what yield is yielding, what type yield is yielding. You can have an int here, but you can have any other type in there being yielded. Long, double, byte. There's this disconnect. That's one thing you have to be careful about. So that's another negative thing about this one. But otherwise, I think it's awesome, because before ranges, we had op-apply. I forgot. What do you use for each loops? Op-apply. So op-apply is actually better in some cases than range algorithms, where you need your stack build up automatically. Because once you go into op-apply, you can call arbitrary depths of functions. But this removes it. Fibers removes that need too. So you can write any range this way yourself. I like it a lot. I mean, I like it a lot because it brings that elegance, I lost it, to tree iteration, this one. Perfect. Other questions?
Why don't you pass the yield function as a parameter to the fiber function as a solution to the type issue that you mentioned?
Yes, so you're asking why not pass the yield function to the series. It can work, because the other tree traversal did that. So we would give it a function and it called the function. Well, it would make it a little heavier, I think.
It would look the same, except inside the parentheses you'd have like yield of int space yield.
Yeah, that could work. But also, you can say, why not use the reference variable either?
No,
Yeah,
okay.
I mean,
I
know what you mean, yeah. Yeah, that could work too. But I mean, try it if you think it's better. We can use that one too. Others?
What more features do we need to add to std concurrency in order to make it on par with the load balancing across threads in languages such as Go?
Thank you. That's another thing I really forgot to put in here. So going back to this extreme simplicity of IP and SP, That's a lie, of course. A thread is not only an instruction pointer and a stack pointer. There's also the thread local storage. Every thread, and especially in D, where I'm going to get to that, every thread gets its own private storage area, thread local storage. And this is a benefit. This is one of the good things that D brings. That's the right default to have. So the question is, Go and other languages benefit from moving fibers from one thread to another. That, unfortunately, doesn't work without thread local storage, or doesn't work well, doesn't seem to warrant the problems that we need to go through. One example is compilers apply optimizations looking at a thread local variable and saying, oh, I can cache this here, even though there's a yield call in between. And then it uses it right here. So cache this variable before the yield and use after yield. But if yield allows this execution context to go to another thread, then that cached value is not the same on the other thread, because the thread local storage is separate. So there's a long discussion. I'm sure you are a part of that discussion, of course. I recognize your frame. Is that Ola? Okay. Oh, Nordlow, of course, yeah. So the current decision seems to be that we don't think it's worth moving fibers between threads. And there are proponents of this idea in this room, I know, like Zunka is over there. So it doesn't really solve, or it doesn't work. We don't think it's worth changing the status in that case. But this is a great hallway discussion topic here. I'm sure we will continue talking about this later. Others?
What if you want to manipulate an array from two fibers?
What if you want to?
Manipulate an array, like removing elements or adding elements, and you use two fibers to access the array.
I think that's all legit, because fibers will not execute at the same time.
But what if you iterate an array and yield?
I'm not getting the question, sorry.
So you iterate over the array in one fiber. Then you yield during that iteration. Then another fiber manipulates the array.
Oh, I see what you mean. Yes, yes. Well, yes, so you have an array where one fiber thinks it's iterating over an array, but another fiber is executed. It starts manipulating the array. The array itself, the element manipulation might be a problem, but changing the array, no, if there's one array, okay, yeah, so that would be a problem. There are actually other problems with the yield approach. Even though I said they interleave main thread fiber, the fiber itself can make a call to a library or some third-party call. And if that function makes a yield inside without the knowledge of the fiber, then you're yielding too early anyway. So there are these issues with fibers. You want to do something, yield, do something else. When you're doing something, the function you called can yield inside too. So I agree, there are issues. Shall we move on? I think fibers are more interesting, but let's go through this quickly. So these are some D features that help with concurrency in general. As I mentioned, data is thread local by default, and we love this feature. You can touch your module level variables without any reason, any need to synchronize. Int A is mutable, but it's not shared. If you want to share, you explicitly say shared int. But now you must be careful, and you must maintain that not only one thread mutates it at a time, or you need to control mutations to that variable. Immutable is implicitly shared, and that's awesome, because immutable means it's not mutable. I don't need to protect it. Nobody can mutate it. And we have this other type, __g shared. That's when you want C-like and C-ABI-like shared data. Again, you must be careful and you must control access to that variable. And the good thing is shared and immutable are overloadable function attributes. You can have an object with two functions, foo, one shared, one immutable, the other one neither. And you can control what type of functionality is operating on your object. Okay, this is an interesting slide after Andrei's talk. Andrei said garbage collector must go, we should not have it. But interestingly, garbage collector actually helps with multitasking. If you have multiple threads and you pass in, let's say, a message immutable into a worker thread, you don't need to take care of that array yourself. No reference counter needed, nothing. You don't need to know who owns it, how many threads are touching it. Once nobody touches it, it's collected by the garbage collector nicely. So this is one of the benefits of garbage collector multitasking. And then D has synchronization primitives. You can mark a critical section of your code as synchronized, and only one thread can execute in that area. Of course, behind the scenes, there is a synchronization primitive working. There's a mutex. There's a locking of that mutex happens. We don't want to do anything like this, because as soon as you have a synchronization primitive, if you remember from the time slice picture, you're abandoning the rest of your time. If another thread is running, the operating system puts you on hold until that lock is available to you. So these are slow operations.
Sorry, about your earlier remark, so the GC does have a number of advantages, and convenience is one of them, and indeed, simple concurrency is another. I forgot to mention that, so, you know, right. I concur.
Awesome. We concurrently concur. So there is another nice feature of the D language where...
Excuse me?
If you want to grab... Oh, sorry.
About that, it's synchronized. As much as I understand it, you only abandon the rest of your time slave if actual contention happens. If there's no contention, you don't necessarily abandon the rest of your time slice. You get access and it works.
So if I heard you correctly, you said only if there's a contention you will abandon your time slice.
Yes.
Otherwise you walk through. Yes, of course. Just like any lock, I guess. So one benefit of the synchronized keyword, you can give it multiple locks at the same time, because sometimes you want to do something only after grabbing both of those locks. It's a common computer science programming example where you want to do it like this at the language level. You don't want two threads waiting for the other lock. Locked A, locked B, and they're waiting for the other one. That's called a deadlock. But D prevents this automatically if you use synchronized keyword like this. And the language also has the classic synchronization primitives in that module, core sync. I mean, that's a package. Core sync is a package, and we have these modules that you may want to browse. But in general, we do not want to do things like this. Not on a server, let's say, server application. So another feature of D, I would say, as we said, in order to share data, you have to mark it as shared. And this direct modification of shared data is now deprecated. If you do this, you'll get this warning, which tells you use atomic op, which is a CPU feature, again, where you can mutate data atomically. Instead of read, modify, write, that whole operation is atomic. So instead of this ++i, you can use import core atomic and use this operation on it, which means it's always a binary operation. So it says I plus equals 1, but the whole thing is atomic. And there are other primitives like atomic store, atomic load, and others in that module. Another interesting thing in core atomic is CAS, which stands for compare and swap. This is also a very interesting primitive which provides lock-free algorithms, lock-free mutations. The idea is very interesting because what you do is, the idea is based on, okay, I have these two threads and they both change the same variable. I need to protect that access to that variable. However, it's likely that no two thread will be interrupted right when you're dealing with that variable. It's actually unlikely if you have long executing code around that. So what you do is, let me try to mutate this guy, thinking that maybe I'm the only one who's mutating. If it works, great, I mutate it. Otherwise, the CPU will tell me. So CAS is a CPU feature. What you do is, you get the current value of the variable into current I, and you say, okay, that's the current value. I think it's 42. Now I'm going to set it to 43. Let me try it. If it works, the return value of CAS tells you, yes, it worked. You thought it was 42. You assigned it 43, and nobody else changed it in between. We did it. You're good, and you continue. If it failed, it means somebody else really changed it, and then you sit in this busy loop, trying again, and chances are it's going to work in a few tries, and without any luck, again, without any giving up, abandoning the time slice, at the expense of a busy wait, which may be arbitrarily long, you change your variable. So this is used in luck-free algorithms and data structures, which is hard, very hard, unbelievably hard. To be entertained, I recommend watch Tony van Aert's luck-free by example presentation or something like that. He goes through slide after slide after slide showing you how you think you have it right. Nope, doesn't work. Let's try this. Nope, nope. So it's a very entertaining way of showing you how hard luck-free the algorithms is. So if you think luck-free is very hard, then try wait-free. I hope you can understand the difference between the two. I don't think I know the difference, actually. It's hard to phrase. But the first wait-free algorithm was finally written in 2011. So correct implementation of stack or something else. Try something else, almost impossible. But we still have CAS, which is helpful. Luck-free is okay, but extremely difficult. And also, another issue, because it's a CPU-provided operation, you have a limit on the data that you can change with CAS. 64-bit, 128-bit, and 128-bit is the tops if you're running on a 64-bit CPU. So then what you do is, if you want to mutate two variables at the same time, you have to bit pack them in a 128 bit-wide data. And we're going to learn about bit packing from our good friend Amaury here on this conference. Probably he's going to mention something related.
Just a short. So lock freeze, there is global progress, and wait freeze, every thread is making progress.
Yes.
So in lock free, some threads may be stalled, wait. And wait free, no thread is waiting.
Yes. I could say that myself, but I'm not sure I know, really. Okay. And then another feature that we appreciate in D is standard concurrency, which uses a tried and true method of concurrency, which is message passing. Extremely simple. You spawn a thread starting on a function, and then you send messages to it. You're not limited on the type of messages, everything. As long as the receiver knows what to do, everything works. But again, this gets into the blocking I/O style. Whenever you have a receive, that thread is stuck there waiting for a message. It may be the normal case for your application. Maybe there's nothing else to do, fine. But if you're on a server, you don't want to wait on such, give me a message to continue I/O. So this is great, but may not be applicable to your server application. Then underneath standard concurrency and standard parallelism, we have the core thread module, which is the lowest level API. If you want to go to that low level, you can do new thread starting from that function. But then eventually you need to invent concurrency and parallelism or fibers yourself. Okay, a little bit input and output now. I've mentioned a number of times you don't want to wait for input or an output because it's blocking. So I/O handling can be on a blocking, synchronously blocking. You can say, I want to read that data, I'm waiting until it comes here. Or you can say non-blocking synchronous. You say, give me the data. Data may be complete right away, or you can get partial data. For example, read gives you just partial data sometimes, so you have to wait for the rest of it. Or it can be asynchronous, which is the preferred method for a server application. What you do is, dear operating system, I want to read this data. Please call me, do this callback whenever it's complete. I don't want to wait here. I want to go deal with other clients here, but whenever that read is complete, wake me up or call this callback. So asynchronous I/O invariably involves an event loop. Your server is in an event loop, waits for events to happen, and dispatches those results. The reactor pattern is synchronous. You're sitting in an event loop, something happens, and you call a callback saying, this happened. So that callback executes, comes back to you. You pull another event, oh, that happened, and you do these things. You call another callback and wait for it to complete. So the better pattern is proactor, where the callbacks are set for completion. You're in your event loop. I hope Zönka and others can tell me if I make a mistake here. You pull an event, you dispatch what it needs to do, and come back to your event. When that completes, you get a callback executed. And for this one, actually, for proactor, for pure asynchronous operation, you need operating system support. And Windows has that. Windows is at the low level, gives you a great asynchronous API. Maybe not great, but it is asynchronous. Linux, on the other hand, does not have proper asynchronous support. So eventually it boils down to, hopefully not select, but epoll, which is not asynchronous itself. So we have libasync, which is available on codedlang.org. This is an async library which handles your event loop, written completely in D, cross-platform, extremely lightweight. Do we have the author of this library here today? Or anybody involved with it? No. However, this library is used by vibe.d. Is that right, Zönka? And asynchronous, and Dragos is there too. So both of these two other great libraries use libasync, so that's our solution for an asynchronous event loop. Vibe.d, can we have a microphone, please, Dylan? Zönka will help me introducing, he's on the second row here. So we have this wonderful flagship framework, asynchronous I/O framework, thanks to Zönka.
Yeah, so we invented that sometime when I don't know, it was quite a few months after I started with D, and we wanted to start a small project, and a colleague of mine, he used Node.js, and we started with Node.js, and it had that callback-based API, and we did that for a few days, and then we were so angry about the results. And I remember that D in version 2, so when D runtime was taken over from Tango, for those who remember, the fiber support got pulled over. So we thought we could combine those two, and avoid the callbacks and get a synchronous API, but still use asynchronous I/O in the back, so that we could get away with a lot less memory if we have a lot of concurrency. Yeah, and from there so it was first a small, just the network I/O stuff and file I/O, and then we added HTTP support, and well, now the focus is more on a high-level web framework and REST frameworks. And hopefully most of the low-level stuff will eventually be discarded and replaced by a Phobos standard solution. But that still takes a lot of work. So.
It's huge, but you can pull out certain little pieces out of it, right?
So start from the bottom and take the really low-level stuff and then work to the top.
Awesome.
Yeah.
Thank you.
Yeah.
And if you could give the microphone to Dragos, please, because the next one is about asynchronous, which is, again, available on codedlang.org, with some differences from vibe.d. Dragos, please.
Yeah, actually, I implemented this because of 3 reasons. In my company, we had some people that, as stays there, it's actually a port of the Python 3 asynchronous library. It's a very nice API that it's really easy to use. And actually, as I said, we had I had 3 reasons to do this. I had in my company some people that already knew Python async I/O, and it's much easier to use the D solution. Then we needed a library and not a framework, exactly as you say, because vibe.d means really to give up your standard sockets and all these things. And then, I had a lot of fun to implement it. Yeah, that's and let's see, maybe we someday vibe.d can use this instead of the libasync. Yeah, at the moment it's based on libasync, but I plan to also have native support in this.
Great. Thank you, Dragos. So the next slide is about a few more libraries that we have on codedlang. Another event-driven library, Callie. Future, of course, very important, very hot topic. You want to set up a future for an asynchronous value, a value coming asynchronously. Then you want to chain other operations as it becomes available. But I haven't looked deep into these myself, and there's a simple feature there. Do we have the authors of these modules here, libraries? No, but check these out too. I think I'm done. More questions? Steve.
So I want to take this opportunity to bash a feature of D that I think a lot of people don't like. In your slide for synchronized with 2 locks, basically that's the comma operator at work. You're only locking the second lock.
Okay, what should I do?
If you go back to that slide.
Yes.
Right there. You're actually only locking lock B
Yes.
and not lock A. Lock A is just thrown away. Because
How is this syntax? Do you remember?
you would do synchronized lock A and then synchronized lock B.
Really? Okay.
I tried it out. It definitely does not lock the first lock.
So do not trust this one. Test first. Awesome. Questions? Thank you. Guys, thank you.